live here. So this means this is our last class on thermodynamics. Celebration next week, and move on to optics after that. And we'll spend our next chunk of time on talking about optics and the models of light that we have. So just by way of reminder, we are going to have PLC 5 is still for Friday. And remember, that's a submission, and that's like a write out on the paper and submit type of thing. We have the lab, so I'm going to look over. Didn't have time last night, but hopefully today and tonight, I'll look over your lab proposals, get back to you, and we'll be ready to go. So the lab on Friday is going to be to hopefully go ahead and get started on stuff and work on the projects for presentations the following Friday. We'll have Celebration 1 on Tuesday. That'll be administered over Canvas. Oops, plus homework 3. That's Tuesday. So we've had a couple of quizzes, and the celebration is going to be basically the same type of thing. It'll be sit down, take it, and submit it, and that's that. Usual type of thing. It'll be open book, open notes. Open notes, and the use of outside stuff, no internet, no talking to friends, no anything like that. So I'll leave you on your honor, and hopefully be good to go. So should be posted up. You should have most of the day, so to find the time to take it. So it should be posted up. Basically by midnight on Monday. So if you really want to take it at 1 o'clock in the morning on Tuesday, you can do that. Other than that, we got a few things to do today. We're going to go through a refrigerator, kind of a quick refrigerator example. Most of the analysis that we're going to do involves the heat engine rather than the refrigerator, and so we did that example last time, and this time we'll do one on the basic workings of the refrigerator, and a little bit of reasoning out with that. We're going to take a look at the more statistical and microscopic version of entropy, and then I guess that's going to be about that, is my guess. So let's go ahead and take a look and get started on what's going on here. So we talked about refrigerators and heat pumps last time. Where the coefficient of performance was the thing we were talking about for the refrigerator and for the heat pump, and it still is basically an efficiency. It's just not called an efficiency due to the idea that in our minds we think of the efficiency as being a number between 0 and 1, and these are not going to be, essentially. So let's suppose that we have a refrigerator that operates between two temperatures, or maybe it's a freezer or an AC unit or something. I guess let's make it a freezer. That way we might make the numbers work out a little better. So let's assume we have a freezer that's operating between a temperature of -3 centigrade and so that'd be the cold temperature, and the warm temperature of the room in a normal setting, 27 centigrade. A little warmer than normal, but an easy room temperature. If I look on the label, I find this consumes power, consumes a power of 200 watts. So what I'm going to want to try and find out is how much heat is getting exhausted by the motor that's running between these two temperatures. How much heat's getting exhausted out into the room. How much heat's getting exhausted into the surroundings, and let's pick a time, maybe in, say, 10 minutes or something like that. During 10 minutes. Okay, so essentially what we have, the usual type of refrigerator schematic. Right? We have our tea hot, we have our tea cold, and we're working with a Q from the hot and a Q from the cold, and as I've drawn it right now, it violates the Clausius second law. So we need to, sorry, I'm just going to try and move you a little closer here. So we need to make sure that we're going to have some work put into this. And now it's okay. The work that's getting put in, though, we don't know, but we do know the rate at which it's getting put in. We know that the power is 200 watts, which means every second 200 joules of energy are coming in order to try and make this heat go the kind of quote-unquote wrong way. So, we know that we have this power, and over time, the heat that's getting dumped out into the hot reservoir, into the surroundings, we could probably figure out the rate at which it's doing that, and then when we multiply by the time, we'll have the total amount of energy that's getting dumped out by the heat, by the engine into the into the hot heat reservoir. All right. So let's assume that we have a Carnot coefficient of performance, right? This is a nice reversible engine. It's a Carnot performance. So let's take these and let's calculate the Carnot coefficient. Due to Carnot. All right. So if I do that, I'm going to find some really good stuff here, right? If I find the Carnot efficiency, for a refrigerator, if you remember, it should be T cold divided by T hot minus T cold. And if I do that, I'm going to find that it's minus 3 centigrade divided by 27 minus negative 3, so that's equal to 30 centigrade here on the bottom. And therefore my coefficient is kind of strange. It's negative 0.1. So this is a very bad refrigerator apparently. And we're going to do even worse as we get going here. No, wait a sec. Wait a minute. What are we doing wrong? I can't have a negative coefficient of performance, right? That wouldn't be quite right. Let's change this into the temperature it's supposed to be, right? If we're using straight T's, we got to use the absolute. If it's deltas, it doesn't matter whether it's Kelvin or centigrade. But here, since it's regular T's, we got to flip this into Kelvin. So if I take a look at this, it's going to be 270 on the Kelvin scale. This is going to be 300. So I should be able to look at TC, which is 270, divided by hot minus cold, which should still give me 30, because that really was a difference. That really is a difference, so the bottom doesn't matter. At least that's going to get right. So our coefficient of performance, the Carnot efficiency here, is going to turn out to be 9. Is that right? 27 divided by 3 looks like 9. So, this is why we don't really call it an efficiency, because having an efficiency of 9 makes your brain explode. And that's a scientific proven fact. So I wouldn't think of it as efficiency if you... Otherwise, just don't say I didn't warn you. Okay, what this means is that if I go back and look now at the refrigerator as it stands here, I'm going to now take the Carnot efficiency and I'm going to link it to the regular efficiency, or the regular coefficient of performance of the refrigerator, which we would have said is what we want out divided by what we put in, and what we want to have happen is the QC. We go QC divided by W, because the W is what we're putting in, and that would be how we want our refrigerator to operate. And if it's operating on the Carnot coefficient here, then that should equal 9. So quite quickly we can find out that QC is 9 times the work that's getting put in. Now, before we go any further, I want to talk really quickly about the coefficient of performance number here. 9, that's a pretty high coefficient of performance for a refrigerator. But notice that part of it is because these temperatures are really close, right? These are within 30 centigrade of each other. And we talked about the amount of money you're putting in. Is it more to run the refrigerator in the summer or the winter? We left off with that last class. And we found out that it was more in the summer because this number is larger. Or, is that right? Yeah, so this number is larger, meaning its coefficient of performance. Its performance is decreased. So, just to revisit the idea of why that is, when the temperature outside is reasonably close to the temperature of the inside of the refrigerator, or even, right, you can imagine the absurd limit of the temperatures being equal. Well, it doesn't cost very much, right, to take a little bit of heat out of here at this temperature and put it over there at the exact same temperature. It doesn't cost that much, okay? And this is somewhat similar, if you've had 4B, this is somewhat similar to taking an electric charge from over here and putting it over here. It doesn't cost you anything, there's no difference. Now, once I take another one and I put it over here, well, now these two things are repelling each other. Likewise, if I put the first piece of heat over here, and now I put a second piece of heat over here, well, the temperature over here is now warmer than it is over here, so I gotta work a little harder, right? Therefore, when these temperatures are equal, it's simple. Just take the heat and put it that way, and nobody cares. So when these temperatures are close to each other, we get a higher coefficient because it's kind of, quote-unquote, easier to move the heat. And you can imagine taking heat from a cold, like we were talking about with the summer months, and trying to put it into a very hot environment. That's going to be very difficult to do. Okay, now, nowhere in here does it talk about power, and that's what I gave you here. So what we're going to do is we're going to have to change these two things into a rate ratio rather than just a regular energy ratio. I'm going to do that by making a silly notation, maybe. I'm just going to put a dot. If I put a dot above both those quantities, now I'm talking about the rate at which those are happening, right? Let's just say that that's happening. So now I'm going to take this, I'm going to reorganize it in exactly the same way. So my rates are related by exactly the same equation. Because if it's true for the quantities, it's true for the rates as well. Therefore, if this is known, this is a power, this is a rate of work being done, and I know what this number is, and therefore now I know what the amount of heat exhausted from the cold compartment would be. It's 9 times this number. And once I've gotten that, I'm going to go back and look at my refrigerator and say, well, look, I know that the energy coming into the cycle is going to equal the energy leaving the cycle. And therefore, the QH that I'm looking for is QC plus W according to my schematic. And now all I've got to do is go make that a rate equation. And I do that just by putting dots over everything. And that makes it a rate. And then we're done. Because in here, I know what QC is, I know what W is, it's 9 of those, or no, QC is 9 of those, and W is 1 of those, so this is 10 W's. Or W dots, I should say. This is 10 W dots. Okay? And so once we know this number, all we've got to do is multiply by the number of seconds in 10 minutes, which is 600, and we'd have the amount of energy that has been exhausted into the room in 10 minutes. And if you knew the volume of the room and the amount of air in there, you could calculate the temperature rise via sensible heat transfer of the air in the room. I wanted to say one other thing about this, and that is if this was a heat pump, then you'd notice again that the coefficient would be slightly different, right? I'd have the 300 over, and it would be even slightly more coefficient. It would be a better coefficient than the refrigerator. So my QH, though, would still be rather large compared to the work I'm putting in, and that's typical. Right, this is actually the hallmark of the heat pump. It is efficient, and if you take the amount of energy, and I think I said this at the end of last class, if you take the amount of energy you would have taken to burn and then get the heat out from combustion, if you had taken that fuel instead and used it into as a heat pump, if you used it to power a heat pump, you would have made it run better. It would have lasted longer, given you more heat. It would have been more efficient. In general, these things are just more efficient than straight out combustion. Okay, so little refrigerator example, and hopefully you enjoyed that. A little bit of hunky-dory. All right. Just take this thing here. Wow. All right, so let's go ahead and take a look at the addition, maybe, or the modification that Boltzmann made to the field of thermodynamics. What he did was, back in about the 1870s, 1880s, he started thinking about what does it mean when we consider an ideal gas and we have all these macroscopic quantities that we're measuring, okay? So we have a macroscopic pressure and we have a macroscopic temperature and a volume, and it's an ideal gas and it's made of gas particles. And we know that the mole number, if we look at the particles,
right? The mole number might be 1 or 2 or something like that. But if we look at the number of particles that it takes to make that amount of moles, it's enormous, right? The number of moles in something is typically near Avogadro's number. So it comes out to be a statistical interpretation of the behaviors of these tiny little gas particles. Because there's so many of them, the macroscopic quantities are basically mean or average behaviors of all of the 10 to the 23rd or 10 to the 24th particles that are zipping around here. And it turns out that we can kind of count what's allowed. What I'm going to do is I'll kind of give you a little bit of a more of a background, and then we'll take a very like a simpler system and take a look at what it means to put some math behind this. So basically the idea of the microscopic properties of a system are related to these average behaviors of these 10 to the 24th molecules or particles or whatever they were, right? Remember, it says 1870, 1880. They weren't totally sure of atoms at that point. So the microscopic viewpoint the microscopic behavior is jumbled, it's random, it's chaotic, right? There's a lot of stuff going on, or I maybe shouldn't use the word chaotic because it means something, but the microscopic behavior, basically the idea is it determines the macroscopic behavior. Such as pressure, temperature, etc.
So the question is, how does it do this? It does it with average behaviors. And if you remember, the Maxwell-Boltzmann distribution was kind of an indicator of the average behaviors of things. We had things like the average, the RMS, and the most likely, or the most probable. So we need to look at the average behaviors of these microscopic particles. And so we're going to make an assumption about this that is kind of one of those things where you go, well, that seems right. What we're going to do is we're going to basically assume that if our system is in thermal equilibrium, then any of the states that it could access are all equally likely. This is kind of related to equipartition of energy, or it's kind of the same mentality, but we're going to assume that at thermal equilibrium, anything is as likely as anything else, any configuration. How do I want to say this? I want to say accessible. Any accessible.
So any accessible microstate is as accessible as any other one. All right, so what does this really mean? When we're at thermal equilibrium, we have the ability to measure these macroscopic quantities, right? Like the pressure and the temperature and whatnot. Does that mean that if I were to make a very, very tiny pressure gauge, then I would stick it into this, maybe it's a box of gas or something like this, right? We're going to put it in here. If it's a very small, very, very small pressure gauge, is it going to always read the exact same number? And I think you can imagine, since the pressure is essentially due to collisions of the gas particles, both with each other and with the walls of the container, and now since I've dropped this pressure gauge in there, it's going to also suffer some collisions. If it's a very small thing, then every now and again it's going to get a strike, right? It's going to hit from here, hit from here, hit from here. So you might see the pressure going up and then down, and up and then down, and up and then down, and up and down. But those hits are so quick for us, we don't notice this, and we can't build a thing that is going to respond quite that quickly. I forget the number of collisions per second, but it was probably over 10 billion collisions per second or something. I can't remember. We did this like a week ago or something like that, and I can't remember back that far. So the idea of any microstate is that it's any instantaneous state of the system, right? Any microstate, meaning that suppose I take the box of gas, right, and it's got a mole's worth of stuff in it, and I say, all right, here's my box of gas. I'm going to put a little divider in it. Okay, like that. And the state of having 6 times 10 to the 23rd particles evenly distributed over here is a microstate. Having all of those 6 times 10 to the 23rd particles on the left side is also a microstate. Okay? Having all 6 times 10 to the 23rd particles evenly distributed, right? That's a microstate. But what if I take the one over here and I swap it with the one over there? That's a different microstate now. Right? What if I take the one here and I switch it with the one here? That's a different microstate. So, my goal here is to convince you that if we assume this is true, then the establishment of thermal equilibrium is nothing more than the overwhelming likeliness that that's what's going to happen, simply by the sheer magnitude of the numbers involved. So that's why it's called statistical, right? It's statistical because we're looking at 10 to the 23rd things, and we're thinking about, okay, if every microstate, every state of the system is equally likely, right? And I'm standing, right, or make this the room, right? And I have a partition right down the middle. I'm standing over here. It's as likely that all of the molecules of air in the room have suddenly come over to this side. Hey, it's equally likely as it is that they're spread out. So the question is, why don't we see all the molecules over here? Well, because when I spread them out, remember how I was counting states. Having them spread out is all one microstate. But if I switch these two, that's a different microstate. If I switch these two, that's a different microstate. If I switch these two, that's a different microstate. So the number of possible states, of microstates, here to have them all spread out evenly is so overwhelmingly more than the number of microstates of having them all over here, which is basically a few. And there's a couple of them, I can kind of switch these around, but basically they have to be over here and not over here. And this is so overwhelmingly less likely that it doesn't happen. Okay.
So that's the idea here. And what I'd like to do is try and put a few numbers behind what's going on here. All right. And just try and see, can we make it such that we can notice some trends when we are dealing with, instead of 6 times 10 to the 23rd things, maybe we're dealing with 2 or 5 or something 10, something a little bit easier to deal with, just so we can get our minds around it a little bit easier. Okay, and you could imagine that you could take this same assumption here and you could think about flipping a tray of pennies, right? You could put 100 pennies out on the tray and then you go whoosh, right? So that you're randomly flipping them over and they all fall back down. What's the likelihood? It's equally likely, right, that they should come up, one of them should come up heads versus tails. It's right? It's equally likely. Therefore, the number of them coming up, the number of states in which they all come up heads, well, there's only one of those. The number of states in which they all come out tails, there's only one of those. The number of states in which they come out almost half heads and half tails, there's a lot more of those. So what I'm going to try and do is count how many total accessible microstates are there. And then we're going to try and count how many microstates are involved in, say, having one configuration versus another, like having all the gas molecules over on this side. If you think of this as kind of a heads-tails situation, right, you can see there's basically only one situation in which all of them are over here, and I die. Unfortunately, that hasn't happened yet. Well, fortunately for me. All right. So I'm going to try and say that if we have molecules on the left or molecules on the right, that's kind of like having a penny flipped come out heads or come out tails. Okay, it's either it's over here or it's over there. So it's a bit of a simplification, I understand that, but it'll help us kind of get our minds around this. All right, and then what we're going to do is we're going to talk about the probability of these microstates and these configurations happening. So let's start by taking a look at how do we count the number of possible states of a system. So let's start with a 4-penny system. And let's count how many possible microstates there are. Alright, so I'm going to start with just 4 pennies, and I'll just use arrows, and we'll have heads be up and tails be down, say. Okay? Alright, so my 4 pennies, I'm going to just be able to write out what are the possible microstates. So for this, I would be able to say I can do this. Right? That's one microstate. And I can start doing every single possible permutation of this. Okay, so I can go to this. And then I can go to this. I'm going to skip to go here. Alright, so I've got all of them up here, I've got one of them down here, I've got 2 of them down there. I can just make columns, I can do 3 down, all of them down, etc., right? So, if I do this, I'm probably not going to do every single one, but we'll get an idea here. Let's do now this, that, this. Right, so those are the 4 combinations possible with 1 tail and 3 heads. Here's the combination with 2 of each. I got this one, that one, that one, this one, I've got this one, that one, this one, that one, that one, that one, this one, this one. Well, let's see, what else do we have? I got this one, that one, this one, this one, this one, this one, this one. Did I do that one already? No. Etc., etc. All right. How many do I have here? I got 2, 4, 6, 8, 10, 12. Okay. Well, now I need to go back to doing 2, 3. So now I can go back to doing ones, and I got to be able to do 3 downs and 1 up. Haven't done that one yet. So that means I got to do 3 downs and 1 up, etc., etc. I'm not going to waste a whole bunch of time doing all of these, but you can imagine I've got a lot of these to be able to get through. In fact, I've only really got 2 more, so let's just do them right now. I got that one, that one, that one, that one, and then what's the last one I've got? It's the middle one, so it's got to be this one. No, I already did that one. I did that one, that one. There's one more. Anyways, you can see it's a 4x4. I don't know which one I'm missing from over here. But anyways, whatever it is. So I have every situation that I can think of, except for this last one, which is going to bother me, but I'm going to move on. I'm going to say I'm moving on. I'm probably not going to. Nonetheless, this is the total number of possible states, of possible microstates of the system. Each one of these is a microstate. Okay? Each one of these is a micro state of the system. All these possibilities. So take a look at what happens. If I count these up, I have only 2 possibilities, ups and downs, and I have 4 pennies. Now if I count the number of states, I'll find that there are 16, and if I look at this, then I'm going to cleverly realize that this is 2 to the 4. Right? That's equal to 16. Okay, so if I go to, right, even if, suppose I just went down to 2, right? If I went down to 2, then 2, that's pretty simple. You'd say I've got this, I've got this, I've got that, or I've got that, right? There's no other possibility. But now that's 2, because I've got either heads or tails, to the number of pennies, which I had 2, so that's equal to 4, and but lo and behold, that works out. And then you go to the 16, and then you go to there. So let's suppose that this is the way you count the number of total states that a system could have. That's 2 to the n, where n is the total number of particles. And the 2 comes about because I'm saying that there are only 2 possibilities. I've got either heads or tails. The molecule is on the left side or on the right side. Okay, so I'm restricting it to basically 2 states. 2 states, or if you like, 2 possibilities. Okay, if we had a situation where it could go that way, or that way, well then this would be 3 to the n. Anyways, we're going to stick with 2. Now, go back to this one. If I go and say I want to know the likelihood that I'm going to get all heads, well, that's 1 in 16, right? Now I want to know the likelihood in which I'm going to get 2 heads and 2 tails. Well, now I'm going to start counting all of these ones, right? I got 1, 2, 3, 4, 5, 6. I should have one more in here. I guess that's the ones I'm missing. I should have about 6 of those. So the probability of getting 2 heads and 2 tails should be 6 out of 16. The probability of getting 3 heads and 1 tail should be 4 out of 16. So if I look at this, what happens is, if I plot this,
what happens is that I start thinking, all right, so I say there's one way to get all heads, there's one way to get all tails. So I'm going to go, all right, one way to get all heads, and then there's one way to get all tails. There's 1, 2, 3, 4 ways to get 3 heads, 1 tail. 1, 2, 3. It's going to go like this. There's 1, 2, 3, 4. Sorry, 4 of those. There's 4 of those. There's 6 ways to do that one. So I'm going up here. And then I'd say, oh, well, I'm back to 3 heads, 3 tails and 1 head, and then I'm back to all tails. So I'm getting this kind of thing looking here, right? Which, as you let n get bigger and bigger, becomes your standard, like, okay? Standard looking kind of regular histogram of a bell shape. And what happens as n gets larger and larger and larger is that this curve actually narrows and it gets very spiky, because this middle one, which is the most likely behavior, starts to dominate, okay? Now, if I wanted to think about, for example, putting a little bit more of a math behind this, what I would do is I would say, okay, the total number of microstates being 2 to the n, and if I look closely at something like this, I'm gonna do a little bit of visual FOIL. At least I was taught it as FOIL, how you multiply how you multiply the binomials. Or is it 2 binomials? I don't know if I'm even using the right language for math, but it's when you do 2 things and you multiply them, square them. What if I did something like this? If I wrote them out as that plus that squared, right? Then I would have said, well, it's this times itself, so I would have done the firsts, the insides, right, the outsides, and the lasts. That's how I get FOIL. And then these two would have had a 2 behind them as long as they commute with each other, right? So that's no problem. I would get a 1 of those and 1 of those. So if I write it this way, it's like it's a head plus a tail to the square, because I got two total pennies. So what happens if I go up and down to the fourth, right? And I square that, right? That's like this thing squared. Then I go through all of this. Now, if you know how to do a quick binomial triangle, these work out really well. These are pretty cool. These give you all the coefficients, so we can count the individual microstates. Or I should say, we can count the number of microstates that make up a configuration, really, I should say. So let's... All right, so then what's a configuration? Well, a configuration is, for example, in the 4-penny case here, half heads, half and half. That's a configuration. How many microstates occupy that configuration? 1, 2, 3, 4, 5, 6. Right? So this is really denoting that there are 6 ways, that is microstates, to achieve an outcome, and the outcome is called the configuration. So if I count the number of microstates in a configuration, if I think of it as a binomial, I can use something that's called Pascal's triangle. And Pascal's triangle, if you haven't seen it before, it's a wonderful little invention. It's basically just adding successive numbers and then spreading them out like a triangle. So if I start with 1 and I go 1 and 1 like this, now all I got to do is add 1 and 1. I'm going to get 2. Oops, I got to go a little further inboard here. I got to get 2 here. I'm going to get 2 here. I'm going to get 1 there. And then I do the same thing here. I go 1, 3, 4, 3, 1. And I'm going to go 1, 4, 7, 7, 4, 1. And these turn out to be, that doesn't seem right, does it? 1, 1, 2. I did too many because I'm not thinking what I'm doing. I'm trying to talk and do math at the same time, which is never a good thing. Let's try that again. 1, 2, 1. There we go. 1, 3, 3, 1. 1, 4, 6, 4, 1. Okay. And then 1, 5, 10, 10. 10, 10, 5, 1. Okay. When you look at this set of digits, look at this one right here. That's this thing to the fourth. This would tell you all the coefficients of the possibilities. So essentially what this is doing is it's counting the microstates in each configuration. Do I want one head? I want all heads? 1. All tails? 1. Okay, what if I wanted 3 heads, 1 tail? 3 heads, 1 tail, there's 4 of those. Okay, what if I wanted half, half? Well, there's 6 of those, right? This is not a coincidence. This is a result of basically binomially expanding that. And this is what Boltzmann started to discover. And you could probably see it, I was like, ooh, wow, this all kind of works, right? It can kind of, all right, okay. So now let's go and take this to an even kind of bigger idea. All right. So if we count the number of microstates in a configuration, there's a number. There's a word that we call that number. The number of ways, right? 3 heads, 1 tail. How many of those can I have? Well, I've counted the number of microstates in the one configuration. That's called the multiplicity. So the multiplicity is basically saying how many different microstates are there in that configuration. And what we can do is think about how to extend this triangle to very large numbers. I got to take this triangle out to 10 to the 23rd. I don't know if I have time for that. So let's come up with a quick shortcut. All right? Let's come up with a quick shortcut. So these numbers are called the multiplicity. Multiplicity is counting, it's how many microstates there are in a configuration. It's basically these numbers, okay, what I just plotted on the histogram here. It's these numbers. So how do we get these numbers for any set of numbers that, right, any set of particles or pennies that we want? How do we get that? Well, you're gonna find out there's a way to do that, and it's called the factorial. All right, so the multiplicity, if I want to generate these numbers, what I have to do is I take the total number of particles factorial, and I divide by the individual numbers that I want, so like 3 heads, 1 tail. If I take, for example, 4 pennies, then I'm going to do 4 factorial here, right? And I'm going to say I want 3 heads, 1 tail. I'm going to do 4 factorial divided by 3 factorial divided by 1 factorial. But 4 factorial divided by 3 factorial is just 4. Right? And there you go. If I want 4 factorial divided by 2 and 2, right, I'm going to get 4 factorial, which is, 4 times 3 times 2, which is 24, divided by 2, which is 12, divided by 2, which makes it 6, and there you go. All right? So you can generate any number in this triangle. You can find out the binomial coefficients with this thing. Okay? And all this was already kind of known about when Boltzmann came along, and he just started to interpret it slightly differently. He started to think, what if I take these numbers and I take the statistical behaviors of this incredibly large number of particles, And I think that it's really just a consequence of the average behavior of these very large numbers. Okay? So here's how you count the multiplicity for each state. Okay? So here's where Boltzmann took a really big leap. Okay? He then ended up saying that the entropy of a situation, okay, the entropy of a configuration is related to the log of this number. Right? In other words, if I think of what's more likely, the more likely scenario, as we see in nature, is that maximum disorder is happening. And that means that when I look at two heads, two tails, that's the one in which I can have I can get the same outcome the most number of ways. Okay? I can get the same outcome the most number of ways. In other words, I have the largest number of microstates possible to make that configuration. How do I get two heads, two tails? Well, I could do it any one of these, all these ways here. How do I get all heads? There's only one way to do that. So that has lower entropy because there's only one way to do it. Now, when I think two heads, two tails, and I look at those microstates, I see that there's a multiplicity of 6. There's 6 microstates that could make up that configuration. Therefore, its entropy will be larger. Okay? Now, go to the silly extreme and say I'm looking at 10 to the 24th particles of air in the room here. What's the likelihood that they all end up on this half of the room? Well, it's not 0, right? But the entropy of that situation is so low that it basically is not going to happen. And the entropy of the situation in which they are all spread out evenly, even if I take this one and I swap it with this one, I can't tell the difference. But this is a totally different microstate. I don't know if you're aware that I just took this one and I took that one, I put that one over there. Now this is a completely different microstate. I've got another, I'm going to just take these two and swap those over. We're in another microstate here. Can you imagine? There are a lot of possibilities of just flipping this to this, and all of a sudden I've got, right? I can take that one from on that side of the room, this one on this side of the room, I can just switch them. That's different microstate. Now I've taken particle number 3,842 and I've swapped it with 9,614,312, and we didn't even notice the difference. Therefore, the multiplicity of them just being evenly spread out is huge, and the entropy is therefore large. This, Boltzmann says, is the reason that systems evolve to maximum disorder, maximum entropy, because it's just overwhelmingly likely. The probability is just much bigger that it's going to spread out and have as many possible microstates that it would have in this situation. It's got the maximum number. All right. So the ultimate, let me go over here. The ultimate thing that Boltzmann came up with is that the entropy is related to the log of that number. It's related to the number, or I should say the multiplicity, because we know it's that. Entropy is it's not the multiplicity, it's really the log of the multiplicity. So I should say is related to. Such that when this is a big number, and I have the possibility of finding many, many different ways of having the same thing. In other words, many different microstates to my configuration, large multiplicity. I said the same thing 3 times in a row right there. Then I say the entropy is maximized, and the thermal equilibrium is a consequence of maximizing the entropy. Therefore, S, the entropy, is equal to the Boltzmann constant times the natural log of the multiplicity, and the multiplicity is known as omega, or if you look in some standard textbooks, it might be W. I don't know why they don't. Maybe they want to confuse you, or they don't want to confuse you with these crazy Greek letters, which is what we've been doing for the past year and a half. So I don't know why they picked now. This is the expression that is on Boltzmann's tombstone. It's so fundamental to the statistical interpretation of thermodynamics that he is recognized as essentially the founder and creator of the statistical view of this. Okay, so let's take a look at, let's see, let's do one other thing here. Let's do one other thing here. I want to talk about the probabilities. The probability of configuration. The probability of a configuration, I'll call it double-legged P with a foot. I don't think I've used that one. We use double legs for the power and we use foot for the pressure, but I don't think I've used double legs and a foot. So that's going to be the probability. All right, the probability of a configuration. So the probability of a configuration, we kind of talked about this already, right? What's the probability of getting 2 heads, 2 tails? Well, we said it was going to be 6 divided by 16 because 16 was the total number of possible things that we had in the 4 penny situation. 2 heads, 2 tails, we came up with 6 of those. So the probability was 6 divided by 16. Likewise with all heads, it's only 1 in 16. Therefore, the probability must be the excuse me, it must be the multiplicity divided by the total number of possible states that we have. Okay? So we'd write it as the multiplicity divided by 2 to the n. Where what we want to do is then add up all of the probabilities and say that we have to reach 100% of, we've described 100% of all the possible situations. And in this case, I think you'd see we would do that because I would take 5 here, that's 10, and 6 would be 16. And that's what we came up with, right? It was for the total number of 2 to the 4th is 16. So the total number adds all the way up, and it's already built in here for you. All right, so we're going to do that where the total sum of these things is equal to 1. Okay. All right. So, having done that, you could imagine that instead of pennies, we were talking about the probability of molecules on either side of the room. And you could go in and look at entropies of these situations, right? What if I did only have 4 molecules? Let's take the 4 penny situation, and now let's say it's 4 molecules in a box, and I have a probability of 2 over here and 2 over here. Or I have 1 over here and 3 over here. Or I have none over here and 4 over here. What are all these probabilities? Well, we've already kind of figured most of them out, right? It's this line of things right here. I've got one state in which no molecules exist over here, and they're all over here. I've got one state where they're all over here and there's none over here. And that's what this 1 is here, and that's what that 1 is right there. So if I look at that probability, it's 1 in 16. Okay. If I want to calculate the entropy of those situations, what's the multiplicity of a 0 with 4 particles over here? What's the multiplicity of this? In other words, how many microstates exist in a configuration in which everything's on this side? Right? Everything's over there. 4 over here, 0 over here. How many microstates? Yep, there's only 1. What's the entropy of that situation? Log of 1, that's 0. Okay? So this is saying it's more ordered than a situation in which I had 2 and 2. Okay? If I look at the situation in which I have 2 and 2, I'm going to take the log of 6 here because my 2-2 situation falls right in the middle of the triangle here. And I'm going to say the log of 6 goes there. And I'm going to have to multiply by the Boltzmann constant. And just for reference, if you don't know the Boltzmann constant, it's 1.38 times 10 to the minus 23. And it's going to have the units of the joule per Kelvin, which is exactly the unit of the entropy. All right. So I would take the log of 6, multiply by the Boltzmann constant, and I have the entropy of that situation. And if I wanted to figure out the change in the entropy, right, I could do that. If I was going to go from a situation of one molecule here, 3 over here, to none here and 4 here, well, I figure out what that, I go this way, I'd figure out that's a decrease in the entropy. So I had to either extract some heat, I had to make this happen, right? I had to do a little bit of work, and then I heated up in doing the work, etc., in order to make something like that happen. Okay, so I'm gonna stop here. Let's do a little review on other things. This is, I mean, to me, this is fantastic. The reasoning and the beauty behind thinking of how this works. And you have to get over, because initially when I was introduced to this, I go like, oh God, statistics. God, no. Who wants that? And the answer is nobody. But when you think of it this way, and you think of the average behaviors of things, really that's all the statistical part that's coming out. It's not actual statistics. It's just it's a statistical interpretation of things. I thought this was amazing, and I still do. And I think this is one of my favorite topics in physics, and we get a half hour on it. So it's tough. It's a tough scene. Anyways, since we have a celebration coming up, I wanted to go ahead and give a quick summary of what we have done to this point. So let's do that. Well, we started off long ago talking about the first law. We talked about 0, 1, 2, and 3, right? And I kind of tried to motivate to you that 0 and 3 we weren't going to deal with much, but there is foundational conceptual stuff that's involved there. However, it's not super important compared to 1 and 2. 1 and 2 is where we've done most of our work. Okay? So we have the 4 laws of thermodynamics. And you can go back and look at 0 and 3, but due to our time, I'll just concentrate on 1 and 2 because they are the more salient ones here. And the idea that essentially, right, you can come back to this equation, and it's like I've kind of been telling you, yes, we've had a lot of equations. What does this really mean? Okay, do not go away from the mentality that first law is energy conservation. Okay? You can have it in this nifty math format and the equation and all this stuff. That's great, but it's energy conservation, and that should stick in your brain. Okay? This is energy conservation. So when I say use the first law to do something, I mean you better be looking at what's the energy going and why is it changing and what's coming in and what's going out and that kind of thing. Okay? So bar charts and piston cylinder diagrams, super helpful with this type of thing. Okay. Law 2, I gave you a couple of different ways of thinking about it. We had the Carnot statement, we had the Clausius statement. And the idea is what's forbidden. Even though first law says some things are okay, second law says not okay. In actual, for example, Carnot, we've spent some time talking about, you've got to have at least a 2 heat flow cycle in order to get work out of a heat engine. Clausius is saying, if energy's going this way and going this way, that's not allowed because this is a cold reservoir and that's a hot reservoir and it's going the wrong way. Can't do that. Okay? Even though the heat flows might be equal and they're going in, and energy is conserved, Clausius is saying, no, that doesn't happen. Okay? So when you think about the mentality of the second law basically gives us direction, right? It gives us the idea that things travel forward in time. Okay, and that's another thing that's so powerful about the second law. When you take laws 1 and 2 together, you can take them out here, and then what we find is that we get this change in entropy. We get the establishment of the concept of entropy, and entropy really helps us define the concept of time flowing forwards. Things don't go backwards in time because that seems like there's going to be a decrease in the entropy because the idea is entropy increases with time. It's always greater than or at the minimum equal to 0. All right. With this all in mind, our goal was to put ideal gas as a thing that we could apply our thermodynamics to, and I think we succeeded somewhat, but I do want to emphasize once again that the real thermodynamics is this. We talked about the applications of it to an ideal gas, but that is just an application of it. So I really want you to keep in mind these things, okay? When we go to the ideal gas, we have a really nifty, simple equation of state that tells us that PV equals nRT. Or if you like, it's equal to capital N times Boltzmann constant T. Again, not a coincidence that Boltzmann constant's in here. And we have our 4 processes, right? This is kind of, right, if you're thinking layer cake here, there's the top. That's the bride and groom, and they're kissing. And now we're on level 2. We're doing the 4 ideal gas processes, right? Constant pressure, constant volume, constant temperature, 0 heat, or slightly, right? Now we can say it, constant entropy. Right? P equals constant. That's the isobar. V is constant. T is constant. The isotherm. And S is constant. And this is the adiabatic one in which Q is 0. All right? So we take those, and those are our 4 processes. And then it's basically working with those. How do we find what the work is? How do we find what the heat is? Right? I'm looking at this thing right here. We come up with expressions for all 3 of these things. We got to know when they apply, and we got to know how to get to them. All right? Thinking of the internal energies, we're thinking about degrees of freedom of the gas. We're thinking about temperature. Right? We're thinking about those types of things. When I look at Q, the heat transferred, I say, well, I can do a straight, like a constant volume process, in which case I can calculate the heat straight away. If I do a constant volume process, constant pressure process, I can calculate the heat straight away. If it's not one of those, I can't go to that nifty little molar way of doing it. Right? Work is basically always the same thing. Negative integral PdV. All right. And after that, a little bit of calorimetry here and there, a little bit of entropy calculations here and there, and we're off and running. So yeah, that's that. I think that's going to be the end of our thermodynamics section for this class, and I think that we are just about at the end of this class for today. So appreciate your attention, and I appreciate your efforts over the past few weeks. I guess 5 weeks, because we're at the end of week 5. So celebration comes up on Tuesday. Be ready for it. It will be nothing that you are not familiar with. It will probably test your readings of the situations, right? You'll have all the tools that you need to attack the problems. And just remember, show me what you're doing. As much as you can, draw diagrams and explain, because if you just start hitting me with equations, that's a way for me to get confused quickly, because I don't know why you're using this or what's going on here. I want to see the physics of the situations, all right? So bear that in mind, and stay strong and do well, all right? Please don't forget to submit homework on Tuesday. There won't be a class. There won't be a Zoom session. It's just going to be go do the celebration. So I will see you for class again on Wednesday next week. All righty? So until then, folks, happy rest of your day. Go be thermodynamically interesting. And we will see you post-celebration. All righty.